Good morning, my dear friends. I hope you are all in a pink of health. So today we'll be talking about the disaccharide lactose. In previous class we spoke about maltose, the formation of maltose, correct? Before we talk about the formation of lactose molecule today, let us understand what lactose is, and on acid hydrolysis what lactose can give us, and later we can go for the formation of lactose, correct? Let's have a look. Lactose is a disaccharide, everybody knows. Its molecular formula is C12H22O11, correct? It is known as milk sugar. It's known as milk sugar because it's found in milk. So that's why it's called as a milk sugar. Now look here, lactose on acid hydrolysis, have a look, gives these two molecules, beta-D galactose and beta-D glucose. This is important. This is very much important. When you know on acid hydrolysis what you get from the lactose molecule, then only you can go for the formation of it, correct? So let us understand now formation of lactose. Okay, on acid hydrolysis it gives me beta-D galactose and beta-D glucose. So formation will be from, okay, how the lactose will be formed? It will be formed from beta-D galactose and beta-D glucose. So let's see. Formation. Let's talk about the formation now. Formation of lactose. Have a look. We need two molecules here. As I mentioned, I need beta-D galactose and I need beta-D glucose. Correct? These two molecules. So that when I make them to react, I should get a molecule called as lactose, which is a disaccharide. I should get lactose. When this will react with this, I should get lactose. And there will be a loss of water because when two monosaccharides react, okay, it's a condensation reaction. There's a loss of water, correct? And second thing is that there will be a formation of glycosidic bond, which I told you yesterday in case of maltose. Here also there will be a glycosidic bond formation, correct? So these two will interact through glycosidic bond and they will lose water molecule during the formation of glycosidic bond. So it will be a condensation reaction because there will be a loss of water and you will be getting lactose. This is the formation of lactose. Okay, let us discuss it in detail how it is formed, correct? So let's have a look. Let me take it out for time being. Let us draw the structures first. See here, first of all, I will draw beta-D glucose. For glucose molecule, everybody should know that we need a pyrrole ring, 6-membered ring. And that 6-membered ring should contain 1 oxygen and 5 carbon atoms. And the 6th carbon in glucose is outside. This thing I have discussed in detail in previous classes. Which form is this? Alpha form or beta form? It's a beta form. So in beta form, OH group on which carbon? First carbon is anomeric carbon. Correct? It should be down or it should be up? It should be up. The OH group, because it's a beta form. Beta form means on first carbon is basically, my dear friends, it is your anomeric carbon in glucose molecule. On anomeric carbon, C1 carbon, OH group should be on upper side. Upper side means basically on left, correct? And H will be down. So my dear friends, I hope you have understood what is the meaning of beta. The position of OH group on upper side. Upper side basically means on left, correct? So this is our beta form of the glucose. Everybody should know this thing. And rest of the structure everybody knows. H, OH, it will be OH, H, and again H, OH, and here will be H. So this is my beta D glucose molecule. If I put this OH group down on first anomeric carbon, then this beta form will change into alpha form. Correct? So this is our beta form. So OH group has to be up on first carbon, which is anomeric carbon. So let us draw the structure of galactose. Structure of galactose is similar to that of glucose. Galactose and glucose structure are same. There's no difference at all. Okay? But there is a change in position of OH group. There's a change in position of OH group at carbon number 4. Remember that thing. Exactly, the structure of glucose and galactose are almost same. But there is one difference at carbon number 4. So I will mention here. Glucose and galactose differ in arrangement of OH group at carbon C4. C4 means carbon number 4. So remember this thing. Glucose and galactose differ in arrangement of OH group at C4. So there is a difference in arrangement of OH group here. Second, third, fourth, fifth and sixth. So here will be a difference in arrangement of OH group at carbon number 4. Glucose and galactose differ in arrangement of OH group at carbon number 4. So let's have a look. I have to draw exactly the same structure, but only difference will be at carbon number 4. Correct? So have a look. Same thing I have to draw. 6-membered ring I will take here. This is also the beta form, so OH group is up. Here also the OH group will be up because this is also a beta form. So carbon number 1. Same thing, H, OH. Third, OH, H. Everything is same. Beta, this is also beta. Second carbon, H, OH, OH, H, H, OH, OH, H. No difference. But at fourth carbon I told you, the glucose and galactose differ in arrangement of OH group at carbon number 4, C4. So this is your C4. So here will be a difference. Here the OH group in the glucose is down at carbon number 4. So what will be the difference? Difference will be, in this case, the OH group will be up and H will be down. So there is a difference in arrangement of OH group at carbon number 4. Look at carbon number 4, it is down and here it should be up. Then only it's a difference, otherwise there is no difference at all. Now the rest of the thing like H, CH2, OH, that is the 6th carbon. So my dear friends, you have learned how to draw the structure of beta D galactose. This thing you are already knowing. Glucose and galactose have a difference at carbon number 4. I hope you have understood. So I will just take down this thing now because you might have made note of this thing. So let us see the bonding in them. Okay, what is the bonding? Glycosidic bond will be there, obviously. Have a look. This is your carbon number 4. Let me draw it. Carbon number 4. So H, and you have here OH. Correct? Carbon number 4. And here now, this is your carbon number 1. Everybody knows that carbon number 1 is known as anomeric carbon. This carbon is here anomeric carbon. CO. Correct? Now yesterday I told you that in glycosidic bond formation water molecule is lost. So very easy it is. So now there is an interaction between, have a look, please have a look. There is an interaction between anomeric carbon, carbon number 1, remember, carbon number 1 of galactose reacts with the carbon number 4 of glucose molecule, correct? So there is a loss of water. So how we will mention this thing? Here we have OH. Can I separate this like this? And let me take it out. So there is a loss of water molecule. Can I mention here minus H2O? H and O, that is H2O, loss of water. And loss of water means which reaction is this? This is condensation reaction. Loss of water means condensation reaction. Now let me draw this particular structure now here for the maltose, because formation will be the, it will be the formation of lactose here, correct? So let me draw the structure of lactose. Can you please focus right out here? So these are the two molecules. Here only we have to see the interaction. This is carbon number 1 interacting with the carbon number 4. So it will be like this. What remains here? Only oxygen will remain here. Hydrogen is gone and OH is gone. What remains here? Only carbon. So now there will be a CO and C bond, because OH and H is gone. So what is remaining here? O. And what is remaining here? Let's suppose H. Now this carbon, if you look here, it has hydrogen also here. This carbon has made, carbon number 1 has made how many bonds? 4 bonds. So carbon will not make any bond. But oxygen has made only 1 bond here. Yes, so it will make 1 more bond. So how to represent it? Have a look. It's represented in this way now. There will be a C1, carbon number 1 will bond with carbon number 4, but through oxygen, because oxygen is there. It will be C1O and C4 bond. OH and H will be lost in the form of H2O. So it can be represented like this. Please try to understand. It's represented in this form. So this is carbon number 1, anomeric carbon. It makes bond with carbon number 4, that we call it as carbon number 4, and this bond is COC bond. Can you see? But the point here is that this corner and this one, they are not carbon atoms. It's just a representation. I hope you have understood. So COC bond, correct? And this is your glycosidic bond. Which bond? Glycosidic bond. Let me write down the rest of the structure. As everybody knows, here will be OH and H, OH, H, and finally CH2OH. Sixth one, can you please focus right out here? Okay. Again, H, OH, H, and fourth carbon, you should see OH and H because it's a galactose molecule, correct? So here you have H, CH2OH, that is the sixth carbon. 2, 3, 4, 5, and 6, correct? Same case here, 1, 2, 3, 4, 5, and 6. Now this bond is our glycosidic bond. And I told you yesterday it's a covalent bond, correct? And it can be also called as, remember, this is beta sugar, this is also beta sugar. So two beta sugar molecules are interacting. So I can also call it as beta. Between which carbon and which carbon bond is formed? First carbon of galactose and the fourth carbon of glucose, there is a bond formation. So I will write down 1, 4 glycosidic bond. So in case of, my dear friends, lactose formation, we have a beta 1, 4 glycosidic bond. But yesterday you have seen in case of maltose, we have alpha 1, 4 glycosidic bond. Please remember it for your competitive exams as well. So maltose has alpha 1, 4 glycosidic bond, but the lactose here we have beta 1, 4 glycosidic bond, correct? Now after that, this is now disaccharide molecule, and the COC bond is called as glycosidic bond, and this disaccharide molecule is known as lactose, milk sugar found in milk. So I hope you have understood the formation of lactose. and it is formed how? When the anomeric carbon of galactose, first carbon is anomeric carbon. First carbon, which is anomeric carbon of galactose, interacts with the fourth carbon of glucose molecule. Okay, beta form and beta form both should be. There is a condensation reaction. Condensation reaction means loss of water is there, and now there is a formation of COC bond. That COC bond is called as glycosidic bond, and it's also known as beta 1,4 glycosidic bond. And please have a look here. Now this is the formation of a disaccharide, and that disaccharide is your lactose. I hope you have understood. Please make note of this particular thing. So my dear friends, we have spoken about the maltose molecule formation from alpha-D glucose and alpha-D glucose. Then we spoke about the formation of lactose molecule from beta-D galactose and beta-D glucose molecule. Correct? In maltose we have seen alpha 1,4 glycosidic bond linkage, and in lactose we have seen beta 1,4 glycosidic bond linkage. Now our third disaccharide is sucrose molecule. It's a disaccharide, as I told you. Its molecular formula is C12H22O11. Okay. When you do hydrolysis, acid hydrolysis of sucrose molecule, it gives me equimolar mixture, means equal amount of. Equimolar means in 1:1 ratio, 2:2 ratio, 3:3 ratio, means equal amount. Equal amount of alpha D plus glucose and beta D minus fructose. We are getting these two substances on acid hydrolysis of sucrose molecule. Have a look. Sucrose on acid hydrolysis, correct? Gives me alpha D glucose plus beta D minus fructose. Now you may be thinking that what are these terms here? See here, this is the optical rotation. And how much is the optical rotation of sucrose? Okay, when you make a solution of sucrose, let us suppose. So obviously you are doing acid hydrolysis, so obviously it will be aqueous only, correct? So when you dissolve sucrose in water, okay, you are doing acid hydrolysis, I mean to say, what will happen? If you pass on plain polarized light through the solution of sucrose molecule, you will find out that it will rotate the plane polarized light in clockwise direction. By how many degrees? How much will be the twist? That will be around 66.5 degrees will be the twist. Correct? So I will tell you the solution of sucrose molecule will be dextrorotatory. So our sucrose molecule is dextrorotatory. Dextrorotatory is also represented by small d. It's also represented by plus sign. So it can rotate the light in clockwise direction. Correct? Which one? The sucrose solution. But once you are doing acid hydrolysis of sucrose, it will break. It will break into the equimolar mixture of alpha D plus glucose and beta D minus fructose. So what is happening right out here? You can see alpha D plus glucose can also rotate. First of all, you are taking the solution of sucrose, and it has been observed that the solution of sucrose can rotate the light in clockwise direction. By how many degrees? 66.5 degrees. Correct? Then you do acid hydrolysis of sucrose. Now sucrose will break. Okay? It will undergo hydrolysis. It will break into two monosaccharides. Now what is this saccharide? Alpha D plus glucose. Another monosaccharide is beta D minus fructose. And it has been observed that in the solution, what happens? This particular molecule, alpha D plus glucose molecule, can rotate the light. This monosaccharide can also rotate the light in clockwise direction. So this guy is also dextrorotatory. Correct? will be represented by D. R will be represented by plus sign. Correct? Now have a look here. If you look at another monosaccharide here, that is beta D minus fructose, you can have a look at the sign, that is minus here. Correct? So that means this molecule is rotating the light in anti-clockwise direction. So I will call it as levorotatory, represented by L or represented by minus sign. Correct? So beginning, if you see, you have a sucrose molecule. The sucrose molecule is rotating the light in clockwise direction. Correct? But after hydrolysis, we call it as acid hydrolysis. After acid hydrolysis, sucrose molecule has changed into alpha D glucose and beta D glucose molecule. Then we found that this alpha D glucose can rotate the light in clockwise direction by how many degrees? 52.5 degrees. And this guy can rotate the light in anti-clockwise direction by how many degrees? 92.4 degrees. Now if I compare alpha D plus glucose and the beta D fructose, these two molecules, which one is capable of rotating the light more? Okay? If you look at the glucose molecule, you will find out that it rotates the light. Correct? But by how many degrees? 52.5 degrees. But when you look at the fructose molecule, it rotates the light by 92.4 degrees. The only difference between these two is that this rotates the light in clockwise direction and this rotates the light in anti-clockwise direction, my dear friends. Correct? Now there is a question. What is the question? I will tell you. These two together, this and this together, are known as inward sugar. Have a look here. Alpha D glucose and beta D fructose, they are together known as inward sugar. I will tell you why. There is a reason. Now look here. I told you that this guy is dextro and this guy is levo. Okay? When we pass on plain polarized light, through this solution, because solution contains now two molecules, glucose and fructose, what is going to happen? Can you tell me? There is actually a competition between glucose and fructose. Who is more powerful? The more powerful is fructose molecule, because it is rotating the light in anti-clockwise direction more, and this is rotating the light in clockwise direction but less. Between these two molecules, who is more powerful? Don't look at plus and minus, just see who has more value, who can rotate the light more. Between glucose and fructose, who can rotate the light more? It is basically the fructose. Fructose is more powerful. Then can I tell that negative is more powerful than positive here? When negative is more powerful than positive, okay? So in this competition, this is rotating light clockwise, this rotates light anti-clockwise, but both are present in the aqueous solution. So there is a competition between glucose and fructose. But in this competition, who is having the more tendency to rotate the light? It is the beta D fructose has more tendency. How much? 92.4 degrees. So between them, what will be the net optical rotation? Can you tell me the net optical rotation here? So the net optical rotation of the inward sugar. My dear friends, I hope you have understood what is inward sugar. Inward sugar means glucose plus fructose together. What will be the net rotation? Who is more? Negative is more than positive. So it will be equal to 92.4 degree. Then you have here 52.5 degrees. Then tell me here, guys, which one is more? Negative is more. So the net value will be negative only. So how much will be this around? This will be around 39.9 degrees. Now tell me, the inward sugar is now levorotatory. I hope you have understood, because there is a competition between glucose and fructose, and in that competition, who is rotating the light more? The light is rotated more in anti-clockwise direction or clockwise direction. Light is rotated more in anti-clockwise direction. So when I calculated the net optical rotation of inward sugar means mixture of these two. So I have subtracted the values here and I got 39.9 degrees, but that is minus, correct? And that is levorotatory. That means your inward sugar is levorotatory, correct? And look at the sucrose. What was sucrose? Sucrose was dextrorotatory. And on acid hydrolysis, sucrose on acid hydrolysis gives me inward sugar. Inward sugar means these two. Okay? And inward sugar is what? Levorotatory. That means you are changing the optical rotation. Like when sucrose undergoes hydrolysis, when sucrose undergoes acid hydrolysis, the optical rotation changes from dextro means plus, and now finally it becomes levorotatory means what? Come on, minus. So this change in optical rotation from plus to minus, okay, during acid hydrolysis of sucrose molecule, yes, that is what we call as inversion of sugar. That's known as inversion of sugar. So please make a note of this. After that I will write down that what is that inversion of sugar. Okay, please make a note of this. So my dear friends, let's explain this term here now, inversion of sucrose. What is the meaning of that? Okay, you know, on hydrolysis, everybody knows this is acid hydrolysis. Optical rotation of sucrose molecule changes from dextro, that is plus, dextro means what? Plus, to levo, which is minus. So on hydrolysis, or we can say on acid hydrolysis, optical rotation of sucrose molecule changes from plus to minus, okay, which is said to be inversion of sucrose. So what is the meaning of this inversion? Inversion means to become exactly opposite, correct? Retention means same, inversion means opposite. Have a look. What was the optical property of sucrose molecule? It was dextrorotatory. Dextrorotatory means it was plus, or we can say it was d, small d, correct? But once it has undergone acid hydrolysis, it has converted, or it has been changed into inward sugar. Now you will be thinking, what is inward sugar? Inward sugar is basically the mixture of alpha D glucose and beta D fructose, correct? And when I just found that the glucose can rotate the light in clockwise, fructose can rotate the light in anti-clockwise, so there is a competition between the two because both are present in the same solution, okay? So who will win the race between these two? Who wins the race? Fructose will win the race, because in the solution which contains mixture of alpha D glucose and beta D fructose, fructose has a more tendency to rotate the light. So minus value is more here, anti-clockwise value is more here. So after doing the subtraction here, you find out that finally we got the value minus 39.9 degrees. That is the net optical rotation of the inward sugar. So this solution, which is called as inward sugar here, mixture of glucose and fructose, has the net optical activity of minus 39.9 degrees, which is levorotatory. So your optical activity is going from dextro to finally levo. So this is known as inversion. So you are going finally from plus to minus. You are going from sucrose to invert sugar. And invert sugar, I told you, what is the value of optical rotation of invert sugar? 39.9 degrees. And that is nothing but L. L stands for levo. So optical rotation is changing from dextro to levo. And this inversion in optical rotation is known as inversion of sucrose molecule, or you can say inversion of sugar. Okay. Now the mixture of alpha D glucose and beta D glucose are called as invert sugar. So I'll mention here the mixture of alpha D glucose and beta D fructose are known as invert sugar. Invert sugar. I hope you have understood, my dear friends. So, in tomorrow's class, I will be dealing with the formation of sucrose, how the formation of sucrose takes place. And obviously, the sucrose will be made from two monosaccharides, and those two monosaccharides will be alpha D glucose and beta D fructose. Once again, in one line, I will tell you what is inversion of sucrose. It means that sucrose molecule was dextrorotatory, and on acid hydrolysis it changed into alpha D glucose and beta D fructose. Those two molecules are present in the same solution. One rotates the light clockwise, glucose is rotating light clockwise, fructose rotates the light anti-clockwise. But there is a competition between the two in rotating the light. So who is more, powerful in rotating the light? Obviously it is fructose. Okay? Fructose is more powerful than the glucose. So the net optical rotation will be minus only. Okay? So and that minus is 39.9 degrees. So now we can tell that the optical rotation of sucrose on acid hydrolysis has changed from plus, that means dextro, to levo, because sucrose gives me invert sugar. So D changed to L. Okay? I hope you have understood. Thank you so much. May God bless you. Yo.